Okay, so welcome to the first talk of the session. I think I will hand it over to the speaker right now. So, do you want to go ahead?
Yeah, thank you. Okay. Okay, so hello everyone. Welcome to this talk. And in this talk, I will present our work on solving the game of NoGo on small rectangular boards. In this work, we weekly solved NoGo played on boards with at most 27 points. So it's NoGo played on 1 by 1 all the way to 3 by 9. And 3 by 9 is the largest board that has been solved to date. So what do we mean by weekly solving a game? It means that we not only want to determine the game's theoretic value of the empty board, but we also want to preserve a winning strategy. Through weekly solving games, we actually had a chance to collect some statistics and discover some interesting properties and human understandable strategies of NoGo. And to accomplish all of these, we used a hashing scheme. We call it sorted bucket hash. My main plan for today is to first discuss some background of NoGo, then I will describe our new hashing scheme, sorted bucket hash, and lastly, I will demonstrate some strategies for playing 4x4 and 5x5 NoGo. So let's begin with the background. NoGo is also called no capture Go or anti-Atari Go. So as you can see by its name, this game is very related to the famous game called Go. And in fact, similar to Go, NoGo has two players, black and white. Black goes first. It has the same concepts of blocks as in Go, and also the same concepts of liberties. But what is different from Go is that all blocks must always have at least one liberty. This means that capturing moves and suicide moves are not allowed. So if you look at the board over here, if it is the white player's turn to play, if the white player plays at the corner, then this is a suicide move. And if the white player plays at E4 here, then it will capture the block of 3 black stones to the left. So this move is also an illegal move for the white players to make. And this non-capturing rule also changed the endgame conditions. So the game ends when a player has no legal move to play, and this player is deemed the loser. So if you look at this board over here, there are 3 empty points on the board, and it is also the white player's turn to play. If the white player plays at any of these 3 empty points, it will capture some black stones. So all these moves are illegal move for the white player. So in this case, the white player has no legal move to play. So the white player loses the game. Okay, here's some previous work of solving NoGo. Bo Xuanshe in 2013 proved that in 5x5 NoGo, all 6 openings are wins for black. This is the earliest record of solving 5x5 NoGo I have found. Followed by that, Tristan in 2020 solved most of the boards with up to 25 points. He offered this solution table in this paper called Monte Carlo Game Solver. And our work solved boards with up to 27 points. So we have the results for 2x13 and 3x9, which is missing here. Next, I will talk about the sorted bucket hash, our new hashing scheme. First, I would like to talk about some motivations for this new hashing scheme. For weekly solving games, we need to preserve a winning strategy in the memory. And by the time the search completes, the winning strategy may preferably reside in the memory so we can extract it. If we use perfect hashing, then we don't need to worry about any hash collisions, which means that we can trust whatever we have stored inside the memory. If we use lossy hashing, on the other hand, then we no longer have this guarantee. And this can be problematic. In fact, we tried with robust hash, which is a lossy hashing, and we encountered many problems. And we also want to be able to solve all the NoGo games with a consumer-grade computer. More precisely, we want to solve all the boards with up to 27 points with at most 32 gigabytes of memory. Okay, after the motivations, I'd like to describe the intuitions behind sorted bucket hash. Imagine that you have an array of buckets you can store things into those buckets. Now you have a game position. Perhaps also you have determined its value. You want to store this game position and its value inside this array of buckets. So a natural question to ask is, into which one of these buckets do you store this game position? You don't want to store everything into the same buckets because that will explode one bucket and that will hurt the performance. I'll come back to this question later. Into which bucket do we store a game position? On this slide, I show the data structure for sorted bucket hash. I'll explain it piece by piece. At the top, there's an array of cubes. Each cube represents a bucket. This array of cubes, you can think of it as an array of buckets we had previously. Implementation-wise, this array of buckets is in fact an array of pointers. Each pointer points to a bucket. A bucket is implemented as a dynamically allocated array. It can shrink, it can grow. Of course, in solving games, the buckets only grow, they never shrink. An element inside a bucket stores some information about a game position. And elements in all buckets are somehow sorted. So here's another question to ask. So they're sorted according to what? I will come back to this later. So here's an overview of the data structure. To put everything together, I will just quickly go through it one more time. So here we have an array of pointers. Each pointer points to a dynamically allocated array. The elements in array store some information about game positions, and those elements are somehow sorted. I guess you have already noticed that there are some numbers here, 2 to the power of 30, 2 to the power of 10. We use 2 to the power of 30 buckets for solving games. It is true for solving all games with board of points less than or equal to 27 points. This is true for all of them. And here we said each bucket stores at most 2 to the 10 nodes. Well, this is only true for 5x5 NoGo. In fact, we will never have a bucket this big when you're actually solving the game. This calculation is really just based on all possible board configurations, and many of them are in fact illegal. So the size of bucket will be much smaller than this number, actually. So let's come back to this question. We have a board, we want to store it. Okay, into which bucket do we store? To determine that, we need to first look at how hash code are being calculated. On the left, we have a board. We encode each empty point as 0, each black point as 1, and each white point as 2. So a board can be seen as a 2D array of 0, 1, and 2. We can flatten this 2D array into a string. We can interpret this string as a base 3 number. Then we can also find the corresponding base 2 number of this string. This base 2 number is basically the hash code. In solving 5x5 NoGo, the hash code consists of 40 bits. We use the first 30 bits as the index, the last 10 bits as the validation code. So let's come back to this question. What is actually being stored in those buckets? What are those elements? So far, I never tell you what exactly those elements are. I just said they perhaps store some information of a game position. In fact, an element holds the validation code and the value of the corresponding game position. You can store more things, but at least you need to have these two. Then a bucket is naturally sorted based on the validation code of these elements. Okay, let's see how sorted bucket hash actually works. A transportation table needs to support 2 operations, find operation and store operation. Find means we want to find some information perhaps we have previously stored, and store operation means we just have a new piece of information available, perhaps a new game position is being solved, and we want to store it into the transportation table. So we have a board, we calculated its hash code, we split hash code into index and validation code. We will first use the index to determine the right bucket this board belongs to. Then we go into this bucket. We may observe there are already some elements there. The numbers shown here are just the validation codes of the elements inside this bucket. Suppose this is a find operation. We can simply do a binary search on the sorted array of elements to locate the right information we want. If this is a store operation, then we can first do a binary search to locate the right spot for the insertion. Then we simply insert the new piece of information into the right spot. So this concludes what sorted bucket hash is, its data structure, and how it functions. On this slide, I show an example of the efficiency gains we can have by using sorted bucket hash. So this is about solving 5x5 NoGo. I listed 3 results here. The numbers here are about how much search effort was spent in solving 5x5 NoGo. For example, Bo Xuanshe in 2013 evaluated 520 billion points in solving 5x5 NoGo. Followed by that, Tristan Kasnav evaluated 46 billion moves, and our solver, SBH solver, it's a solver using SBH sorted bucket hash as its transposition table, together with 2 heuristics to solve 5x5 NoGo. We evaluated in total 3 billion game positions. So as you can see by the number, our solver is more than 2 orders of magnitude more efficient than She's work in 2013, and more than 1 order of magnitude more efficient than Kasnav's work in 2020. I would say this is a huge improvement. That was all for sorted bucket hash. Now I proceed to talk about some strategies for playing 4x4 and 5x5 NoGo. In 4x4 NoGo, the white player wins. Yes, the second player wins. The strategy for the white player is simply, one strategy we discovered is to play symmetrically. Here is an example. If the black player plays at the corner at A1, then the white player, the symmetrical play should be played at A4, should be played at D4. In this case, the white player can make this board symmetric. We discovered that among all the board configurations where the white player can make a move to make the board symmetric, 85% of the time that this symmetric move is actually a winning move. More notably, in the 3 possible openings, the only winning move from the white player is the symmetric move. All other moves are losing moves. So this result is very interesting because it may tell us something about solving 6x6 NoGo. Perhaps 6x6 NoGo, the white player perhaps is the winner, and it may be also true that playing symmetrically is a good strategy for playing 6x6 NoGo as well. In 5x5 NoGo, the black player wins. A useful strategy is making eyes. Well, it is not a surprise because, after all, NoGo is a very similar game to Go in many concepts. We found that in a solution of A1 opening, 45% of the endgame position contain any eyes. This number confirmed that making an eye is indeed a useful strategy. What really surprised us is that often the black player can win without them. So by looking into our solution, if you recall, we are weekly solving those games. So we actually had a database. We discovered another strategy, which is to create long blocks that separate the opponent's stones. Here you can see an example. The long strings of black stones in the middle forms a single block, and it separates the opponent's stones. It separates the white player's stones. Here's a list of something I did not talk about, but they're in the paper. If you're interested, you can go read the paper. Most importantly, something you may be interested in is, for example, the implementation choice for sorted bucket hash and some performance analysis of sorted bucket hash. We have more interesting findings on 5x5 NoGo. We also provide the solutions of linear NoGo or 1x(n) NoGo with n less than or equal to 27. We have 2 general results for 1x(n) NoGo. Okay, as for future work, if one wants to solve larger boards, and perhaps because of the memory constraints, it may be preferable to use 2-tiered approach. Basically, it means we don't have enough memory. We want to use memory and disk to store information, to store the game position we have solved. So SBH works perfectly well with that, but we welcome any ideas to make it more efficient, of course. And also, there's another point here. So we can try to improve the efficiency of the find and store operations of sorted bucket hash. So that's the end of my presentation. Thank you.
Great, thanks very much. If there are any questions, people can chat their question now or.
If there are no chats, then I have a question. My name is Jaap van der Herik, and you talked about, I would say, winning games, and you talked about also that in the same game with different constituents, you could have a draw, you could have a loss and a win, yes? But could you characterize that also in, I would say, technical terms for the game? For, I would say, uneven lines or for I would say special configurations or whatever. So could you, I would say, translate the setting of being a win towards the, I would say, terminology which is used by the players?
Okay, I'll go back to this slides. So a win basically means so this is a game. So as you can see by the rule, since there's no captures or no suicide, so a point placed on the board, it will remain on the board until the end of the game. So unlike Go, there can be captures, points being removed, but for NoGo, points remains there. So we're trying to slowly fill up the board. And if a player has no legal move to make, then this player loses the game. And on the other hand, the other player wins the game.
Yes, that I understand. Okay, that's very good. That is a good answer to that. But that's depending on the configuration. That's quite clear here to me. But if we start with a beginning position, let's say not this configuration, then is it depending on the fact that this is a 5x5 board? And is it the same for a 6x6 board, or is it not just the other way around? So what is the, I would say, the influence of the board size, and what is the influence of the configuration?
You want to see the what?
Now, first of all, does the board size for 5x5 have the same or similar results as the board size for 6x6?
Well, actually, I expect we haven't solved 6x6 yet, but I expect 6x6 is perhaps the white players win, meaning the second players win. So, but in 5x5, it is the black players win. So, I would say the results can be very different.
If that is, I would say, a difference, then of course, then the question is, I would say, prone for further elaboration. That means how about the 7x7 board or the 8x8 boards, or how about the 4x4 boards in relation to this
Oh,
series?
I see.
Yes.
Well, at this point, I do not have a general result for that. It's pretty much like the scenario in Go here. So we have solved 5x5 Go, and we are solving 6x6 and 7x7, but we don't know we don't have a general result, say n by n Go, who will be the winner. We do not have that yet.
The background of my question is, of course, which I remarked earlier with Mueller's talk about, I would say, when I said about 4 in a row, yes? And
Yes.
then I made the remark by Victor Alles. He thought it was a Zugzwang game. And the other games, the win for the first player, is an initiative game, as you understand. And so that is one characterization. But probably, I would say, the characterization of Zugzwang is, of course, it is true, but it is, I would say, it occurs sparse than I would say, the initiative. So I would say, interested in what is the background of the difference between these two concepts.
Thank you for your question, Jaap. I want to move on to some of the other questions because we're running out of time.
Yes.
So,
okay.
Question here from Chushuan Shu. Is the proposed approach specific to NoGo that you used, or is it applicable to other games as well?
Oh, yes, it is applicable to other games. This is basically a general hashing scheme. You can use it for other things, not even in games specifically. Great,
thank you. Ingo Althofer asks, how strong are the NoGo bots in the Computer Olympiad?
Well, this is a SPH solver. It's a solver, so we are trying to solving the game. We can make it into a player by using the solved database. So we haven't tried in Computer Olympia, but if you have this player using the solve database, then it's a perfect player. It will win.
So you have not got a player right now that uses your solver.
We actually had a player which play 5x5 NoGo, and we tested, and yes, it will make perfect move.
Okay, thank you. Frank Lance asks, what makes SBH so much more efficient? Do you have any intuition for why it's working so well?
Well, I guess one possible reason is because of the property of NoGo is that NoGo, there are so many transpositions, and as the game goes deeper, the transpositions actually increases. That's why we have using a transposition table. In this case, we can store everything, but then we can capture all those transpositions. We can avoid redundant search. That's why we have more efficient. Of course, we are using 2 heuristics as well. They improved our search also greatly.
Okay, and there's another question from Peter van Emden-Boas. Is the factorization you used 2 to the 30th and then 2 to the 10, is that an optimal factorization? Did you try other ones?
I didn't try other ones, but I guess this is the most natural one because just consider how much memory we have, 32 gigabytes of memory, and 2 to the power of 10. So if you do, since we are using binary search in each bucket, right? If a bucket holds 2 to the power of 10 elements, then in fact at most we are doing 10 probes, meaning that because binary search is the logarithmic on the side of the bucket. So I think 10 probe is reasonable. If you think of other traditional hashing schemes such as Zorbist hash and you use it together with linear probing or chaining, then it's about the same. Like you set the boundary to 10.
Okay. And question here from Steve Kroon. It seems you need to convert a ternary representation to a binary representation each time you hash. What is the impact on performance compared to Zobrist hashing, which does not depend on board size?
Well, I would say the performance can be we can make it to not depend on the board size. For example, we can pre-calculate all the exponents, and every time you have a move, you just figure out, okay, where this move will reside in which digit it will be in the hash code, and you just multiply that digits by the corresponding exponent and add it to the previous hash code. That will give you the new hash code for the current board. Right?
Okay, great. And last question from Jacob van der Pol. What were those performance numbers of SBH precisely? Why was lower better?
Okay, so this describes the search effort. Let me go back to the slides. Here. Okay, so this is really how much search effort the program will spend on solving 5x5 NoGo. Of course, if you just think of it like we have so many game positions. If we can evaluate as few game positions as possible to determine what is the real value of the board, then it's better, right? We don't want to waste our time on useless search or spend our time searching useless board. So SBH solver, the number is smaller, meaning that it is better.
All right, great. Thank you. Thank you very much. I'm afraid I guess we're out of time now, so I think we're going to move on to the next talk. So thank you very much for your talk.
Thank you.
Well done.
All right, I'm Todd Neller, and in this work to strongly solve and find human playable strategies for the Great Rolled Ones game. This was joint work with Quan, Nguyen, Pham, Phan, Linh, Phan, and Cliff Presser. So we're going to start things off here with, let me get the screen up. So in this talk, we're going to first share the rules of the game and the optimality equations for the 2-player game, our solution method for those equations. We'll look at optimal compensation points, which we could also call COMI, as in Go, and for fairest play. and visualization of the optimal strategy. We'll also be presenting one simple human playable policy that does surprisingly well against optimal play. The Great Rolled Ones game is a Jeopardy dice game for 2 or more players, though, as I said, we'll only be considering the 2-player case. It's a Jeopardy dice game, also called a push your luck game, where the primary mechanic is to make roll-hold decisions, where rolling is taking a chance to secure greater turn progress or perhaps lose all of one's turn progress, whereas holding secures that turn progress. It was first published in 2020 in book form by Sam Mischke and Randy Schoeneman. It's similar to the dice game Zombie Dice, and both are Jeopardy dice games in the 10,000 Jeopardy dice game family. So the rules are relatively simple. You play with standard five dice. The ones you see pictured here are still standard dice, but with the these monster pictures substituted in for the ones. And these are the undesirable numbers to come up. At the beginning of a turn, a player will roll 5 dice, and any ones that are rolled are set aside, and any non-ones are added to a player's turn total. And the turn ends when either the player decides to hold, that is to stop rolling, or they have rolled 3 or more ones during their turn. In that event, they end the turn with no score change. A round consists of each player taking 1 turn in sequence. And when any player ends their turn with a goal score of 50 or more, that triggers the last round of the game. And at the end of the last round, the player with the highest score wins. Now, the rules in the book give no indication of a draw possibility. So we assume for our analysis that a player is constrained to attempt to exceed the score of the current leader in the last round. As an example, if we start out with player 1 rolling a 1-1-3-4-5, the 2 ones are set aside and the 3 non-ones are added to the turn total to have a turn total of 3. Then if the player decides to roll again and rolls 2-2-4, no ones are set aside and the 3 non-ones are added to the turn total to make 6. Rolling again, if player 1 gets 2 ones and a 6, those 2 ones are set aside for a total of 4 ones, and that's greater than or equal to the 3 ones that end the turn with no score gain. So the turn goes to player 2. Let's suppose player 2 rolls 4-4-4-4-5. No ones are set aside. Their turn total is 5. They decide to roll 4-4-4-5-5. No ones again set aside. Turn total is now 10. Third roll, 1-1-2-4-5. 2 ones are set aside. Only 3 non-ones are added to the turn total for 13. Player 2 decides to hold, and their turn ends with a score gain of 13. This 13 will never be at risk. The only thing that is at risk in the game is a person's turn total. So player 2 is locked in 13 points for the rest of the game.
All right. Based on the example round, so there are 2 optimal equations we need to consider. You can see there's a risk of rolling a 1, so we need to find the probability of rolling a 1s. So in a non-terminal states are described within 5 tuples, P, I, J, K, O, with P denotes the current player number, 1 or 2. I is the current player score. J is the opponent score, and K is the current turn total. And O is the number of roll ones that has been set aside. And now we need to find the probability of rolling ones, and let P new ones, taking parameters of D, which is number of dice we are rolling, and new ones, O new. So O new has to be within the constraint of 0 and the number of dice we have. So next bar,
You can use the mouse roller as well.
And next one we want to find about the probability of player 2 exceeding player 1 score. This is a very special part of this game's characteristics, since your player 2s have a chance to exceed player 1s even when player 1s has reached the goal score. And that PXC denotes the probability of player 2 exceed the player 1 when the player 1 score is larger or equal to 50. Taking two parameters, which is delta is the score difference of player 1 and 2, and O is the number of roll one set aside for players 2 turn. And the PXC is 0 if the player 2 has 3 or more ones dice set aside, and PSC is 1 when the delta is less than 0. So when the player 2 already exceed player 1, or else we just recursively compute the new probability of getting a new ones and the PXC of the new ones we gain from rolling another 1. So next we need to find the probably winning with a roll. So when winning with a roll, so it's under assumption that optimal play. So thereafter we have the PXC. Taking the PXC if the player right now is player 2 and player 1 has exceed the goal score, which is 50. So they have to exceed the player 1 score. Otherwise, we'll find the probability of rolling new ones and the probability to win at that particular state. But if the roll has 3 or more dice set aside, now we compute the other player probability to win when they roll. And a player will never hold at the beginning of the turn, so they will never hold when the turn total was 0. Thus, we want to find the probably hold under the assumption of optimal play. So P hold will be 0 when the turn total is 0, or when it is player 2 and the opponent score is larger than 50. And P hold will be 1 if the player is player 2, their score has reached more than 50, and their score should be larger than the first player also. Otherwise, we want to find, if we hold, we want to find the probability to win, probability of winning of the first player or the other player. So then the probability of winning can be assumed in the optimal play is we compute the maximum of rolling or holding, so depending on what choice we make. And now, so the equations are solved through dynamic programming. So these two equations are cyclic, so it's solved to the variation of value iterations from the initial arbitrary p value, which is 0, and then we just substitute the estimates in the equation from the right-hand side, and we just continuously recompute it until the maximum change to the probability is less than the value on the screen.
Next we will talk about the first player advantage and compensation points, which is also common. So we know that when player 1 finished with like 50 or above, then player 2 has no other choices but have to like exceed player 1 score. By doing that, player 2 has an advantage of like knowing what score needed to win. Therefore, with like both players having optimal play, player 1 and player 2 has a winning gap of like 10%, where player 1 has a lower winning rate compared to player 2. Therefore, we want to introduce Kami, which are the compensation points designed to make like the game more fair. In our games, we suggest that player 1 should start with like 3 compensation points that will bring player 1 win rate up to like around 49.55%, and making the gap between two players reduced to around like 0.9%, which is almost like not that bad, right? So here we will introduce the roll and hold surface, where which show that like when a player should hold or when a player should roll when we have some kind of conditions like player one score, opponent score, and a turn total in a turn. So basically when we have 0-1 set aside, player one, as you can see at the beginning, the surface is a little bit like steep because it is player one want to like aggressively reach the goal of 50 at the beginning. At a later stage of the game, when it already reached like 50, player one want to make like their score have a significant leading score compared to player two. So it would try their best. Player one would try their best to go as far as possible. But for player two, at the beginning, you can see player two seems to take less risk, and player two only want to like maintain a good like distance compared to player one score. But at the later stage of the game, like both players want to win the game, right? So it will start to roll until reaching like 50 points. And when player one already reached like 50, player two has no choice. So as you can see, player two will try to like keep rolling and rolling until it exceeds player one. Let me show you the like it just doesn't work. Okay. So next we will move on to the case where we only have like one dice one set aside. So this is a little bit like much more complicated compared to when having 0 dice one set aside, because at the beginning you can see like both players seems to take like less risk, and but still player one still take a little bit like more risk compared to player two because it has some kind of disadvantage. But at a later stage, both want to reach 50 as soon as possible, so both still will keep rolling until they reach like 50. And still like the same as the previous case, player one will try to reach above 50 as much as possible in order to keep like a good distance compared to player two. And player two will continue to roll and roll if possible in order to win when player one has reached like 50 points. And next we will move on to the case where we have like 2 dice set aside. So in this case, it is very risky because if we unfortunately have one more dice one set aside, or then we will lose all our turn total. So at the beginning of the stage, both players are very careful and they take almost like very little risk. As you can see, like they usually hold at around like 5 or 2, but at a later stage of the play, player one of course want to win, right? So it will start to take a lot of risk and in order to reach like 50. And layer two, just like the same, it will start like it will keep rolling until it exceeds player one. So from here we can compare a little bit. For when having 0-1 set aside, both player like seems to take more risk because so the curve is like very steep for both player compared to the other cases. Player one always take more risk compared to player two because it has like a disadvantage compared to player two. And when the more one dices they have, the less risk they are gonna take for themselves. And
Skip this, go on to the policy.
okay. So this is the policy, right? So we want to introduce our simple player and one cases policy, where it will help reduce the winning gap of two players from around 10% to only 2%. So for player one, they will always roll with 5 dice. Before, when they have 4 dice, they will start to hold at or beyond the goal with a lead of at least 20. For player two, if player one has reached the goal score, player two has no choice but have to exceed it. Or if player two has reached like above 50 already, they just can hold and win. And in the other case, player two will keep rolling until we're gonna have 4 or 5 dice. And with 3 dice, both players should hold if it reached the goal score or when the turn total is at least 5.
Yeah, so this achieves only a 2% gap against optimal play. In conclusion, we've computed strong solution of this optimal play for all states of the Great Rolled Ones game. We found that 3 compensation points awarded to the first player make for greatest fairness. And as you just heard, a relatively simple human playable strategy has only a 2% gap short from the optimal win rate. So we can take questions.
Thank you very much. If people have questions, please chat them or pose them. So here's a question. Go ahead.
Yeah, I mean, the quick answer is that I don't know what would happen if the turn order was player one, player two, player one, etc. It's an interesting sort of question, and it essentially would make it so that a person could take greater risks, for trying, over 2 turns. They'd know that they'd have that kind of budget to either exceed the score, but I honestly don't know what it would look like. Other questions?
Well, maybe you can substantiate the 2% gap. I mean, it is of course good that you have the observation, but what are the advantages to give the 2% gap a chance towards, I would say, running the risk of losing?
So the 2% gap that's described here is that the approximate win rate of a simple player in one's cases strategy is 49% against optimal, which is pretty surprising given the non-linearities and subtleties of the optimal roll hold boundary. And yet a very simple strategy performs very well against it. We actually, in the paper, you can find not only that, but 3 other strategies that have a range of different gaps. The one that was not in the paper that would have taken too much space to publish, we got it down to a set of rules with simple arithmetic and cases that achieved a 0.5% gap to optimal. So there's a trade-off between complexity of the human play policy and its performance.
And the complexity, is that easily computable or not?
Well, by complexity, I mean that, if we look at the at different policies, if we were to put them in code, the simplest is just always roll with 4 or 5 dice, holding when you win. Having fixed values that you hold at is more complex. The one that Linh described is a simple player in one's case, and this one is in the paper. This is a 1% gap, but quite honestly, this involves memorizing more cases and more constants than I would care to memorize in order to improve my win rate by just 1%. So the 0.5% gap would take even more, not quite double the number of rules, but such that I wouldn't expect anyone to be able to read it on a slide.
This answers my question perfectly. Thank you very much, and congratulations with your team. They all of them, all members gave a very good presentation. Thank you very much.
David Flatlin asks whether this approach can be generalized to other similar roll or whole games.
And the answer to that is yes, that over the years, Cliff Presser and I have published a number of papers for different Jeopardy dice games that make use of the same general technique. In the future, we hope to push for even more complex rule sets and state spaces.
Great. Thank you very much. I believe our session is finished now. Thank you very much to the speakers.